So I'll read through this question, and then we'll get right to it. It says that an Egyptologist discovers a new pyramid with a square base, and he wants to report the volume. The pyramid was designed to be half as tall as the base is wide. And the base is measured to be 1,000 feet with a maximum error of a half a foot. That's actually not too bad for a maximum error, I think. Estimate the maximum error obtained in using the measurement of this base. Calculate the volume of the pyramid. Estimate the relative error of the calculation as well. So we have this pyramid. It's got a square base. Let's say it's an X. And what else does it say? It says that the pyramid was designed to be half as tall as the base is wide. So what's the height of the pyramid? Right, which in this case, in terms of what I've written down here, people 1/2 that is, right? Now, one of the things that I hate, but just out of curiosity, does anybody know what the volume of a pyramid is? This is one of the things that we'll get to. Oh, good. Yes, this is true for pyramids and cones. It's a third of the base area times height. And like I said, you'll be able to do this directly in the height. So the volume of our pyramid is 1/3. Base area in this case is X squared, and the height is 1/2 X. Right. So the formula for the volume of this pyramid that I discovered is 1/6 X. If I agree so far. I can explain. That's right. Right. The base is a square. But okay. So I've got that information covered. It says the base is measured to be 1,000 feet with a maximum error of 1/2. Estimate the maximum error obtained in using the measurement of the base, 1,000 feet, to calculate the volume of the pyramid. So if somebody asks me what's the volume of the pyramid, what am I going to do? I'm going to stick 1,000 in there for X. You can agree? But I could be wrong, because maybe this is 1,000.5 feet, or maybe it's 999.5 feet, right? Go either way, and that's going to change what I get here. So the actual error is the change in volume as we vary X from 1,000 feet plus or minus a half. So as we so 1,000 feet is where I'm going to compute this, but it could be as much as 1,000.5 feet or 999.5 feet. And if I really want to get the exact answer, I would compute both of these and see what the change in volume is. But we're out in the field in the dust with Indiana Jones and all this, and so we just want to kind of do a quick calculation to estimate this. And so we do this. And this is probably kind of another thing here. What is DB in this case? A half x squared, that's right, that's the important piece. There's something else we need to tack on. Half x squared. Just like doing a U substitution. If this was a U substitution, D wants to say Q, we would say dV, one half x squared. Here's another kind of thing. This change in volume, a change in volume should be in cubic feet, right? There's a difference in volume. It's volume. If you don't have that dx, you're now in square feet, right? You need that dx also. Now, to make this an estimate, we need to know numbers for this. So what's the relevant value for x? This one's 1,000 feet. It's what we measure. And what's dx? This is the change. So 1,000 feet is what we measure, but how much can we miss about? Yeah, it's plus or minus 1/2. Because this is how the x changes, right? This is x. I measured. I got 1,000 feet from my x, and this is the change in x. This is how much I could have screwed it up by. Half foot either way. Right? So now I can make almost something that I can do in my head. This is 1/2 times 1,000 squared times plus or minus. This is 150,000. Right, 1,000 squared is 12. Right. So that's a million divided by 4. Well, I could have missed about 200,000 feet. That sounds like that state, right? Well, this could be relevant there. This is the other one, the relative error. The maximum delta V, this is how much we could have missed by. Delta V over V, that's my relative error. This is theoretical minus experimental by theoretical. I'm going to approximate this by dV over V. Now my dV is 1/2 x squared dx. And my V is 1/6 x cubed. Okay. Notice I didn't put any numbers. It's actually do the album up to a certain point. This becomes 3x over x. So this is about and I'll just take the plus version of this. 3 times 1/2 over 1,000. that relative error is, right, 3 parts to 1,000. So even though this looks big, it's really not, right? 250,000 feet, that's not quite as big as probably, right? Because, I mean, that's just 60 feet by 60 feet by 60 feet. Actually, it's, a little bit more than that, not much. Right, and compared to the fact that this has got 1,000-foot base, this is actually a pretty small amount of volume. This spot, percentage wise, this is a 0.15%, right? Like I said, when I took chemistry and I had lab experience, I never got less than a percent error. Okay, any questions? Any questions about any of this stuff here? What we did? Okay, other questions? Same thing. Okay. Uh, the volume, the volume of a liquid in a cup is given by the formula V of X is the integral from 0 to X of A of Z dZ, where X denotes the depth of the liquid and AX is the cross-sectional area of the liquid at height X. By the way, this is true, and this is something else that you would see in Calc 2. You don't need to derive that here. I've just given it to you. If the evaporation rate of the liquid is proportional to the exposed surface area of the liquid, show that the depth of the liquid is decreasing constant rate. Okay, so this sounds intimidating, I think, the problem does, but it's not so bad, really. So what's given to us? It says the volume of the liquid in a cup is given by this formula. So you've got some kind of cup here. And it could even be one of those fancy pub glasses, right? Or this. And it don't really know this, but it's kind of cold here. As you fill this up, you have a cross-sectional area at height Z, A and Z. This is another useful thing. But really, what is an integral? It's a limit of the sums. So how do you get the volume? You just add up all these thin slices of area, right? And that's essentially what this formula is saying. It's saying, take all my cross-sectional areas, like there's slices of bread in a loaf, and add up their cross-sectional areas in the volume. But you don't even really need to know this. So what else does it say? So when I go from 0 to X, integrating the cross-sectional area, then I get X, so that'll be this volume. Volume is what's up there. If the evaporation rate of the liquid is proportional to the exposed surface area of the liquid, then show that the depth of the liquid is increasing at a constant. Okay. There's a lot of words there, and it doesn't seem like there's much to go on, right? But let's try to interpret this. The evaporation rate of the liquid. Okay. This is one time that units might have think so. What is the evaporation rate of the liquid in terms of what I've got written down? And what would you think of the evaporation rate? What was supposed to use? What is evaporation? Liquid turning into gas. So the liquid leaves my cup, goes flying off somewhere else, right? What's changing about the crap in my glass? The volume is decreased. Right? So the evaporation rate, I would expect this to be in volume per time, something like cubic inches per second, something like that. Everybody agree with that? In terms of the stuff I've got written up here, what do you suppose the evaporation rate of a liquid is? What's changing when water is evaporating? Well, that's indirect, right? That is certainly true. When it's evaporating, your mix is getting small. But what's the main thing? I mean, we did say evaporation, that's the first thing. Well, it's the change of the volume with respect to time. There's your value. The VDT, change volume with respect to time. That's what's going on in your glass, right? The water is evaporating. And what did it say? The evaporation rate is proportional to the exposed surface area of the liquid. This is almost like common sense, right? There's going to be a lot more water evaporating off of Lake Michigan than Lake Hartwell, because Lake Michigan's got a much larger area. There's a lot of area evaporating. That equation. DDT is proportionate to, well, that just means some constant, right? When I say some proportionate to, it means a multiple of what is the exposed surface area? What's on the bottom exposed to the sun? Come on. In terms, this is right, okay. Show that liquid. Okay. I do have a question for volume. Volume is integral. Point x, I guess, integral from 0 to x of a of z. Use the fundamental theorem of calculus. B prime uh, uh, Okay, so here's what I have. I have this right here, and I know that, evaporation rate is proportional to, the exposed surface area. So, if I DET this, then let's be careful about what I'm doing here. This is d prime of x. Big derivative, whatever that is. That's derivative of what's inside. And this is what think of it as. Derivative of what's here. But what is this thing right here? This whole thing right here is also dBdt, because that's what I did. And this is A of x. Yes. Well, what is dBdt? It's this. So at the end of the day, what I get is AX dXdt is equal to K. AX. And remember, K was just this constant of proportionality. But we said the problem was is the evaporation rate is proportional to the exposed surface. Now, assuming the cross-sectional area is not zero, which is a reasonable assumption. What does this equation tell me? It tells me the depth of the liquid X is change in X with respect to time is constant. So if you're in the desert, suppose you have a drinking straw. It's this tall. You plug up the bottom, put water in. Not a lot of water for this drinking straw, right? Now suppose you also have the option of having a glass. We'll assume you're from here it is. A glass of water that's like maybe a fifth as deep as the straw, but it's 1,000 miles wide. If you want your water to last long enough under the effects of evaporation, which you cut too big, you have to pick straw because the decrease in depth is constant. So this is going to finish up. That's sort of counterintuitive, right? And Of course, this assumes that this model works, which there'll be various, but, I mean, if your cup of water is big enough, it'll probably create some weather, right, like Great Lakes or something like that. But within reason, what you want is a hollow cup, because that will save water less under the effects of that pressure, than a short cup that holds a lot of water. Okay, any questions? Did you see what you needed to see on that? Okay, other questions? What did you all find the most difficult about the last quiz? So I had those four integrals, and then we had a max min with 12 square feet of material to make a box, maximum volume, and then a sketch the curve. Actually, I want to kind of need to sketch the curve. I think this is one that takes a lot of work now sometimes. So on this sketch the curve one, I gave you the function x1/3. So we have and then I also gave first two derivatives for this, which were 4 minus 5x squared. Right, and then second derivative. Well, I got these for the various derivatives, and I also said that the roots of this polynomial approximately plus or minus 2.6. Right, so that's the information. Okay, first of all, let's observe this function here. I always kind of look out and try to think what's the domain, what can I plug into this function? Because I want to be aware if there's going to be something like horizontal asymptotes, or not horizontal, vertical asymptotes, or plus discontinuity. Where does this function go? What values of x can I plug in this function that I'm coaching? Yeah, for the function itself. Well, let me reverse the question. Is there anything that I can't plug in because zero is good. 0 times 4 2/3. Would everybody agree that I can plug anything on one of this? Right, that's the user keeper being positive. And then I can plug anything 4 minus x squared, then I take it to the 2/3 power. There's no harm in that. So it looks like this function, whatever I draw, should be continuous here. Right. Okay, so let's start looking at critical numbers. How about the first derivative? So what are? Plus my two, and what else? Square root of, right. And there's one more. I want to mark this up, 0. Plus minus 2 here. Right. Yes. These two, well, I should say these three. Um, there's something qualitatively different about these first three vertical numbers. Well, right, that's certainly true, but what I mean is there's something different about the derivative. There's something that I should call it. What do critical numbers tell you? There are places in the domain of the function where derivative is what? One or the other, either 0 or doesn't exist, right? What happens here? It don't exist. What happens here? Derivative is 0. So I kind of know what this looks like. It should be the top of the it should be the top of the amount at the bottom of the valve. On the well, or it might not be a max remain at all. Here, on the other hand, I expect something funny. Vertical tangent of cusp, something like this. Right? So keep this in mind. This will help you draw the picture. For the second derivative, what numbers do we need to concern ourselves with? Well, this making that 0, and also we get these same things that are making the second derivative. Well, okay, so let's analyze it. The first derivative, got what, 5 critical numbers? 0. See this thing's a smidge less than 1. Minus. Okay, so let's be careful. F prime, notice in the derivative, this piece is always positive, right? Because it's to the 2/3 power, this is always going to be positive. So I don't have to consider this. Well, I'm trying to figure out my side. All right, what happens when I'm beyond 2? Something like 3. Negative, negative. So it's what happens when I'm between 2 over radical 5 and 2? Something like, for example, 1. Because 1 is actually a little bit bigger. 2 over radical 5. I get negative, positive. How about something between 2 over the radical 5 and 0, something very, very small, but still positive. Very small, still positive. I get positive, positive, positive. What happens on the other side? What happens is it's very small, but negative. Well, that shouldn't affect anything. It's still going to be positive, positive. How about something between -2 and -2 over radical? So, like -1. Oh, I see. Square this off, so that should be the same result. It should be negative. And what happens when I have a huge, huge negative or negative 100? That's going to be negative, negative. So my function goes to this: it's decreasing, 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 decreasing. So I get what? A local max -2, and whatever I get when I plug in -2 do. So that's going to be 0 lines. Now on this side, I get a local min. This should be a local min. And for the -2 over the radical 5, and whatever I get. But here's what I know. What do I know about this number? I didn't bother. I could put it in here and figure out what the number is, but I do know something important about this number. What is that? It's negative, right? Because in -2, 0, I will max and then go down. So this one is negative. This is a local nothing, but I do know it occurs at 0, 0. Right? 0 is easy to plug into this particular. This is a local min, local max at 2 over radical 5, and actually it'll be minus whatever the opposite is. Okay, so that gives me a pretty good perspective on this. What about my cavity? Let's see, once again, I'm going to find critical numbers, but this time, critical numbers not really turn on each of this, but this time they're on the outside of the plus minus 2. 0, 2, 2.62, -2, -2.62. Let's see if I can figure out what concatenate is here. Notice this time, this one is always positive. Because now this one's a sort of uneven power, so to speak. So let's see what happens. What happens if you're way the heck out to the right, like 100? This is certainly going to be positive because X4 dominates. And that's going to be positive, so what happens if you're in between 2 and 2.62, maybe like 2.5? Well, since 2.62 is the root of this now becomes negative, right? Because it was positive, the large values, and it passes over this root single root. But you can test something like 2.5. This comes down to negative. It's negative, positive. So what happens if you're in between 2 and 0, so it's something like 1? Well, this should still be in the negative range of this, and if you put in 1 in, you get 10 minus a large number, minus 96. This is negative, still positive. Negative. What happens if you're in between -2 and 0, something like -1? Still the negative range of this, so I get negative, negative. And this one right here between -2 and -2.62, this is still in the negative range of this. This is negative, so positive. And what happens if you're way the heck over on this side, negative 100, say, back to positive, negative. So this is concave down, concave up, concave up, concave down, concave down. By the way, there's a certain symmetry to this problem that would help as well. Does anybody know what the symmetry is? This is actually an odd function. And that's why you see the symmetry here. So notice these are the same that you pan out. And these are opposite as you pan out. And it's because it's not. Well, so let's see what this looks like. So in the final bit, let's see if we can draw this thing. Okay, so conveniently, I know this goes through -2, 0, 0, 0, and 2, 0. Well, let's see what happens. This should be a local min. I'm sorry, this is local max. And this one should be a local. Now, what happens to my function? Well, it increases until it hits that local max. And it's sad most of the time. Then right before it hits that local max, it becomes happy. And after the local max, it stays happy. Right? So and the derivatives in time. I remember that. So what happens now, it comes off of this, so now we're at -2. My concavity stays happy until we get to the origin. And I go down and then up. So I should go down and up, back to the origin. My concavity is happy. And then as I go to the origin, it becomes sad and still increases. What do you think happens to the derivative at the origin? Vertical hand. That's what. So when you come off of this, it's happy and it stays happy until it gets here. It changes concavity here from happy to sad, which is smile, and sad, right up, that's over. And it hits its local. Comes in here. Happy, 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 sad. So this is about a gray scale, 2/5 negative. And it should be, actually, it should be less than halfway here. But, what we have here is vertical tangent. There's a horizontal tangent here, both of these. And then after you pass through 2 here, you're always increasing from now on, and you're continue unhappy for a little while, within the Prozac exam. So that's about as good as I can draw that. But okay. Everybody see that? Okay. Other questions? Sure. I've got it on the screen. So
Like number two, a, just.
Oh. Okay, so let's hit that up. Okay, so yeah, so we'll look at 2A first. This is this limit. So what do we got? Trying to find the limit. As x goes to 0. The interval from 0 to 5x squared. Cosine t squared over x squared. Okay. Anytime you face a problem like this, what's the first thing to do? Direct substitution, and I think I've awarded you for doing it in one of the examples. You just do it that way. What happens if we plug in x equals 0? I have 0 on the bottom and 0 on the top. It's the only zeros. So this sounds like a job for what Paul's doing. I'm sure that's right. Easy part. Derivative of x squared is 2x. This is the fundamental theorem of calculus. So what's the derivative of this? It's the derivative of cosine. Plug in the top to this. So that's going to be 25 x4. Everybody see how I got it? 25 x4. Times derivative of what's up top, which is 10x. And then minus plug in the bottom times the derivative of the bottom. What's the derivative of 0? Derivative of any constant is 0. So the other terms. What should we do now? Well, I can tell you what you're going to get if you plug in, right? Aren't you going to get 0 over 0 again? But, you know, well, let's do some out. See something cancel. Please do not overlook this. L'Hopital rule. That's right. L'Hopital rule turns into death on a hot plate. You don't do some algebraic simplification. This is going to be, well, the 2x look against the 10x. Right? And now you just plug in 5. Here you go. Cosine 0. Where are we talking about?
The first, yeah.
Yeah.
I think that's 0 instead of.
I'll plug in 0. X is 0, you get 5 times 0 squared.
Oh, okay, you think about it.
Yeah, I see what you did. You don't plug in for t, plug in for x.
Oh, okay.
So is that?
Yeah, yeah, I didn't.
Okay, so what else we got?
Did you wanna?
Well, anything's game. Well, here's one where I'll. Files for. That's good. Now, I'm not saying that. Even if that square root weren't here, even if the square root weren't here, looking off was a bad idea. Because to whittle this down, you're probably gonna need to take at least 8 feet of ribbon. Right, which there may be some simplification that happens, but it's still gonna be nine. There's a much better way to do this. This is, I'm not gonna say this is one where you can't. But if you start to look tall from here, you're gonna make an unfolding mass. Certainly, it seems justified if you have infinity over infinity. Now, you can take the root of this, you get 17 power, but this is gonna be a mass change. Right, and it's gonna be very. What's the biggest power that you see on top? What's the biggest power on the bottom? It's half 36, sort of, right? It's 1/2 power. So what I will do is I'll multiply top and bottom. Now, that's easy enough to implement. Top. Five plus 12 over x 5 minus 14 x 8 plus 5 over x 15 plus 1 over x 17 plus 4 over x 8. And look at this whole clump of crap is going to go 0. Now the problem here is x to the 18th they fit in so quickly because square root. Let me rewrite this. Everybody agree with that? 1 over 8 x to the 18th is the square root of 1 over x to the 36. This is going to be 2 plus 5 over x to the 16 plus 1 over x to the 26 plus 1 over x to the 28 5 x 36. Right. And as x goes to infinity, all the stuff goes 0 except for this. Okay. By the way, let me get one. So you see how I saw that it's 5 over the square root of 2 just by looking at it?
Yeah.
Right, because 18th power, sort of 18th power, and it should be the leading coefficient 5 in the square. Close to this. Why negative? That's sort of right, you just be super careful. So your intuition about radical 7 of the 3 is correct, this is base power sort of one here, right? But there's no way, because the square root of 7 is a positive number, right? And when x is a large negative number, it's positive or negative, so it's negative. Let's see what goes wrong. I'm gonna multiply top and bottom by 1 over x, just like I did 1 over x. Now on the bottom, it's easy enough. On the bottom, I get but again, I've got to fit this in the square root, so what can I replace this 1 over x? What's that now? Is that the same? Like that. Is that the same? It is not. Where does x go? If it's going to negative infinity, it has to be walking in the garden of negative numbers. Right? 1 over x is negative. What can you say about the blue thing? It's always positive. This is the absolute value. This is always positive. Makes sense. Now it's the same. Right, okay. That's the subtlety. That's where things are different. So when you multiply this through, you get negative 7 plus 1 over x plus 1 over x squared. And this comes to negative 7. So yeah, so it helps. You'd be close if you said radical 7 of 3, but you missed by a sign. You don't pay attention to what's going on the problem. What's going on the problem is, looks like radical 7 over 3, but very large values of x, this is positive, yet it's negative. There's no way you're getting a positive limit by taking a limit of a bunch of negative numbers, but you can do 0. Now here's one that you really what's this? Actually, that's very good. It is 1/3. If you try open talk, well, you get infinity over infinity, so open talk is worth a shot. This becomes 2x minus sine 2x plus 4, derivative cosine minus sine. The derivative left side is 2. And on the bottom, I get six x plus one. And then I get this product, cosine x, cosine three x. And then I get minus three sine x, sine three x. Okay, well, if you do this again, you get infinity, because that's going to infinity, that's 2 plus or minus 2. And this is going to infinity, and this is small. So you might call it go again. Next step, see that you've got trouble. The next step, which you get is limit as x goes to infinity. On top, I get 2. And then I get minus 4 cosine 2x. I'll take yet another bit of this. And on the bottom, I get 6. And I get some points. That's going to take through 2 product rules. So I get minus sine x, cosine 3x. Then I get minus 3 cosine x, sine 3x. I get minus 3 cosine x, sine 3x. And I get 9 minus sine x cosine x. Well, no, you're done now. And I'll tell you why, because the limit here does not exist. Because what happens is this number right here is floating back and forth between +4 and -4. Right, so this fraction here, the numerator, is going back and forth between 6 and -2, splitting back and forth. Whereas the bottom, I think you know what this is, but all these things, one. In fact, this might even become singular. But this is just wiggling back and forth, whereas this, actually, this is yeah, like singular. But this does wiggle back. But right, this. When you, so L'Hopital rule only works if at some step in L'Hopital rule, you either get a number or you get infinity or minus infinity. When you get one of these wiggly things, that means L'Hopital rule can't be used in the first place. So how do we do this if you can't do it this way? So this means tall, tall. So let's go back and look at this. And actually, looking at this critically might have avoided the problem in the first place. Like you said, this was 1/3 start out, and that is correct. What made you see that?
It kind of like that. So it's based on bottom.
Right. Right. So if this wasn't here, I think we'd all see this just like that other third, right? And this really makes no difference because really this is floating back and forth between x² + 1 and x² - 1. Right? So this is just almost like x² plus minus. And this is 3x² plus x, and that's floating back and forth. And so I will take this with the same approach as we did the other, multiply top and bottom by the dominant power. So this is limit x goes to infinity of on top I get 1 plus cosine 2x 4 squared. And then I get 3 plus 1 over x plus sine x sine 3x over x. This goes to 0. And these two also go to 0. Does anybody know what theorem we have that makes these two go to 0? Can I squeeze it out of you? So notice that, for example, cosine 2x plus 4 is between 1 and minus 1. So when I divide this, as x goes to 0, both of these go to 0. So this goes to 0. And there's a similar argument. Everybody okay with that? Okay, what else we got? Sure. Which one? One B, what cosine x over sine squared x plus 1 from 0 to power of 50. Okay. Okay. Good, just straight up definite interval. How are we going to tackle this? I would recommend this. Bring up any fraction parts of this is really obvious. Right, because how you going? So let me demonstrate. So how would you see the parts here? Okay, good. Want to make sure that it would have to be this and this. Be part for something else, but anyway, the point is the UDV needs to put back together and be that. So don't write cosine with sine squared plus 1. It has to be 1 over that. And I don't know about you guys, but I don't know about that group. I would, for almost any fraction, I would try substitution first. Anybody see heat substitution that might be easy? So, okay, what heat substitution do I do? Yeah, I mean, I see that, but I would start with something simple. What's that? Why not? I mean, that might not be completely what you want to do. In this case, it is, right? but at least that gets us rolling. And here's the beauty, if you do that, what is your DU? So in the substitution, you've got this problem solved, that's DU, right? That's a big piece of the accomplishment, and so you can actually do this. This is the interval, DU over what? And what else do I have to do? Don't forget this step. You gotta change the limits, right? What's the new bottom line? I would say. Good. In the old days, x is 0 and sine of 0 is 0, there's your bottom. In the old days, x is power 2. So you're talking. Oh, that's a serious part of this right there. Anybody know an antiderivative for one over used for this one? Good. I see a lot of you all are like, at this point, you'll put back the x. You've changed the limits. There's no point doing that. Leave it at u. That's the whole point of changing the number. It's now, you don't have to go back to x. So this is inverse tangent of 1 minus inverse tangent. And this is 0 and that's pi over 4. I would accept the answer in this one. Look at the exam from last year. So I asked you 5 integrals. Which ones, if any, would you do by parts? So you tell me, look at exam, last year's exam. So there are 5 plus A, B, C, D, E. Which of those would you do by parts, if any? C, I would definitely do C by parts. What about you? I would do E. Those were the other 3 I would do by substitution. Actually, you don't even need substitution on A. What do you do on A? The first thing you should do is take the square root of x and write it as x, because that's just there, that's go. But what strategy should you take with your A? This was nothing. Just multiply the freaking thing through, and then you'll have powers of x. Just can't do it. There, you shouldn't even need to do it. Yeah, multiply through it. You shouldn't even need to do a substitution. Okay, so for example, we'll do those ones. So you identify these parts. 1 to 3 of x log x. Okay, so that's one of the problems. So the prescription that I heard is parts, and I think that's a smart way to go here. If we do parts, what's your U and what's your DV? What's the biggest, scariest piece of that you can integrate easily in your head? Can you? I would say X. And don't forget DX. This is why parts work well with logs and inverse functions in general. Okay, so I'm going to pick it this way. And when you put this back together, you should get this, and I do, X log X.
But you, it was same thing.
You get the center black, actually. So, well, here, I'll show you. We can go. So. What's the U doing here? And what's V? So this becomes UV minus the cross interval. Remember, parts doesn't change your limits. It's not a substitution. So this is 1/2 x. When I multiply these. So this becomes 1/2 x squared log x minus 1/4 x squared by so end game, I get 9 halves log 3 minus 9/4 play 3. I'm playing the when I play in one, the log goes away. And so I get 9 halves log 3 minus. Any questions? Now, to answer your question, so that's a good question. What happens if I don't feel play? Well, there's a couple of things. I think what would happen is if you don't get away with what, or try something else. So the idea was to try this. Certainly that looks legit because this times this and you back here. So I'm dividing this up into parts correctly. Okay, here's the problem with that. What's the end of the ring? Back to what that is. Know what I'm talking about? Well, I haven't put it the same. But still, you know, I don't know. Because for me to actually do this, I would have actually, if I had been teaching this and I had forgotten, I might have to sit down and do this with my points. But let's just get beyond that. So what I get is x times x log x minus x minus the crossing. Let's so let me clean this up a little bit. Now, so what I have is x log x of the x is equal to. I'm going to clean this up a little bit. X squared log x minus x squared. And then I'm going to get minus integral of x log x x plus the integral of x. And I got this from this pretty side here. It's minus the integral root of x log x plus the integral root of x. So I get x log x dx. X squared log x minus x squared. This thing becomes plus 1/2 x squared minus x log x. It works. Because I'm going to bring this over here. This is going x squared log x minus 1/2 x squared. Or in all its glory, x log x. X is 1/2 x squared log x minus 1/4 x squared. And that's the same. I would opt on the other. And still just I'd solve it. All right, I've got one for you. I want you to tell me what's wrong with this. By the way, you know what the answer is. It's log x. Well, let's suppose that we put parts on that. Derivative minus 1 squared. Yeah. B is x. And so it's going to be two things. 1 minus the integral of three. It is the integral of 1/x dx. 1 plus and subtracting this antiderivative from both sides is 0. Folks, one of two things. Either I tricked you, or it's time for you to change the negative, right? Because let's just prove 0 1. So all this stuff I just wasted time solving the crap. Please tell me something. Everything I did was right. That's how did I do instead? What did I actually physically do with the computer? Oh, I didn't plug anything. I just subtracted. See this symbol here? This is the antiderivative of 1/x. I subtracted it to both sides. Here's here. Here's here. That's subtracted. What does this mean? This means the antiderivative of one over x. Agree? How many antiderivatives of one over x are there? Are you sure? Give me an antiderivative of one over x. Natural log of x is one. Give me a different x. Now that's just the function itself. Give me a, so one of the antiderivatives is one over x, log x, right? Give me another. Something's different, it's log x. What's the derivative of log x? Is that the only function derivative is one over x? But any other function derivative one over x? You're thinking too complicated. What's the derivative of log x plus one? Heard about that? Or that's right. What's the derivative of log x plus two? What's the derivative of log x plus eight? This is an antiderivative of one over x. This is an antiderivative of one over x. There's no reason these have to be the same. They could vary by constant. This might be log x, and this might be log x minus one. Right? We can explain zero equals one. When I took this step here, I subtracted off the symbol. The symbol means an antiderivative one over x, but two antiderivatives one over x do not have to be the same. And that's where we get that foolishness. Okay, other questions? All right, well, before I give you the quiz for today,